First of all, thank you for being here this morning in a holiday. It must not be easy, so I appreciate it. Felipe Monteiro, I work as an applied scientist at AWS. And for those of you that don't know, AWS has a team, a group of researchers called Automated Reasoning Group, where we apply all of the techniques on formal methods, formal verification, a field across all AWS systems, and even within other parts of the company, like Amazon itself. And I've been working with them for over 5 years now, more or less. And it's really nice to see that at the beginning, there was this push to try to deliver value to them, meaning that we wanted to show that there were a lot of techniques in our field that was worth investing and putting into production. It could bring high assurance, high security for all of their systems. And now, I am really happy to say that it's not the case anymore that we needed to convince them. Now, everyone within these groups at AWS is looking for our team or creating their own automated reasoning group to apply those techniques across the software chain. And the one technique that I want to talk about today is software model checking, focused mainly on C and Rust programs. And we develop like a methodology that we're still improving today, and we deploy it across many softwares, not only within AWS, but for the community as well. So this is the first disclaimer that I wanted to do in my talk. Everything that I'm going to talk about today, including the softwares that we use, the projects that we verify, everything is open source. So all of you could access, use the tools, see the proofs that we make. Everything is out there in the wild. And especially, we have deployed those techniques in a bunch of really impactful projects. So for example, we have FreeRTOS over there, where is one of the most used real-time systems for microcontrollers. And it has adopted our proof methodology across 14 of their projects. Everything is open source in C. We have those two, S2N TLS and S2N Quick. S2N TLS is an implementation of the TLS protocol that is used across all major AWS services. If any of you has used Netflix or anything that is built on top of AWS, you probably interacted with S2N TLS. And it's using our proofs as well. S2N Quick is another protocol, but this time implemented in Rust, also adopting our techniques. We have Hi-Fi Time, which is a timing library using satellites. We have Firecracker, which is a micro VM, micro virtual machine manager that is used across AWS Lambda and so on. So I really encourage you to take a look not only at the tools that we use, but also all of the proofs that we develop in the wild. Okay, and I wanted to say that from the beginning because this is a really important point of the talk. Every single proof artifact or property that we check in those softwares, either C or Rust, is integrated into continuous integration, meaning that once we prove a property over the system, this property needs to be checked on every single code change. So we can ensure that the properties will remain true after the system is evolving, right? And this for software is really important because software is an evolving artifact. It would change over time. So we needed to think about how we can develop a proof methodology to ensure properties over software that can cope with a living thing that will change over time. And as you can see in those checks, this CI Kani is one of our tools being checked on every code change. Okay, so let's dive a little deeper. What is this methodology that we developed over the past 7 years to apply software model checking at industrial scale, okay? So the first thing is that we use two model checking tools. We are dealing here with bounded model checking. The first one is CBMC, which is focused on C verification. It's widely known, it has over 20 years in academia. And it combines model checking, symbolic execution, and encoding everything into SAT and SMT now with some support. The second tool, which we have been developed for the past 3 years or so, It's called Connie, which is focused on doing bounded model checking for Rust programs. It's built on top of CBMC. It collects it translates MIR, which is an intermediate representation language from Rust, and it sends the verification problem to CBMC again, doing the same thing, model checking, symbolic execution, and encoded the problem into SAT, okay? The technique that I'm going to talk about today, it was published in 2020 in this paper, code level model checking. So you can take a look and see some of the points that we learned back then. What I wanted to highlight today is some of the learnings that we had in this paper that we are continuing to build upon. It's like the key factors of success applying this technique into the software development workflow within AWS. But in the paper, there are a few other points that I think it is worth to take a look at. So the first thing that we observe is that whenever you are dealing with proofs, you need some sort of a specification over your system, right? And this creates a burden for the developer because sometimes you need to use a separate specification language. So we try to decrease this burden by writing code and a specification in the same language that the developer is already working. So all of the specification that we do for our system is either written in C or in Rust. Of course, this has a problem in our community, right? You lose expressiveness. How can you actually express specific properties? For example, I give you two examples here. Heap layout or the use of quantifiers. You can do that in C or Rust. But we observe that even lacking this expressivity it's paying off for the ease of adoption because no developer wants to learn a separate language. Not only that, if the specification is in the same language as the software, it provides easy integration. The code and the specification living all together. On top of that, it helps with maintenance because, as I told you before, everything should be in CI. Everything should be together with the code, so the developers need to maintain those specifications. If they are in the same language, it decreases the burden there as well. And there's another thing. Some logical relationships, for example, for all elements in this array, this property will be true. We can create some verifier built-ins, and for those who are familiar with svcomp, you already deal with some of those built-ins. At the surface level, meaning that we can provide those as predicates for the developers, so they think it's just a function, but indeed the verifier using with a logical semantic behind it. So let's take a look at one example here today. So this little piece of code, I promise that I won't show you too much of that, is from S2N TLS, that TLS implementation that I mentioned at the beginning of the presentation. This is the definition of a data structure called stuffer. So S2N TLS, it encrypts the data, performs the S2N handshake, and so on. And all the data that is carried across the wire is using those S2N blob structures and S2N stuff structures. It's just a stream or a buffer of data, okay? When we declare this structure, you can see a blob. We don't need to see the definition of this. It has a collection of cursors defining int and a collection of flags. How can we write a specification for that piece of code? So here, if you see from a developer perspective, this is only a C function that doesn't change anything in the structure, it's const, but it performs a few checks. It returns a few Boolean properties over the data structures. We can ensure that the structure is not null. We can ensure that it's a valid blob as well. We can perform an implication. If the stuff is growable, it was allocated before. All of these is specific, and then we can establish some properties over the cursors that they respect in a specific order. The importance of that is that this, from a developer perspective, is just a normal predicate, a C function. But for us in our community, for a verifier, this is a type invariant. It's the definition of all properties of that data structure that should be maintained across operations, okay? Another nice thing of that is that these now, of course, will be used in our proof methodology, but also it could be integrated into their own code as pre and post conditions, as you can see here. These preconditions will check that the operation in every function will operate over a valid stuffer, something that they know that is true. And then at the end of the operation, we can check again if the operation, if the implementation didn't affect the validity of that structure. This can be checked with unit testing or any tests at runtime, but it can also be used within proofs. And that reusability on proof artifacts, it's also a selling point for developers, okay? At some times, these can be very cost for production, meaning that they cannot afford the performance penalty of checking that out every single time. But in a few cases, the security bar is so high that those checks are included even in production code for them. Okay, so now, how can we integrate those specifications into the development workflow? And the methodology that we came up that was most familiar to developers, it was a unit test-like syntax, meaning that any developer would know how to write unit tests, right? We tackle function by function in a code base, and we check a few properties over that operation. In that case, we wanted to do something very similar for proofs, right? So here, but then there is we call a secret sauce, like the differentiation factor of using proofs over the usual testing approaches, is that we can define non-deterministic values, non-deterministic inputs that are not concrete values. So for example, if you wanted to test a function that adds 2 numbers, you can test for 1 and 2, 1 and 3, or a few integers, right? When we are using non-deterministic values, you wanted to inject into the function any possible value that can fit into an integer. And then when you are performing symbolic execution, you wanted to explore all possible paths. And in that case, you have a proof of a certain property for that function. In this one, this is how they write, we call proof harness for a specific function in their code base. So the first thing that they do is to set the non-deterministic inputs. Here they are setting up non-deterministic stuffer. Here is interesting. I don't know if everybody can see, but there is a variable called size of uint32, which is not assigned to anything. That indicates to the verifier that this value size can have any given value that fits into a uint32t type. Okay? And that is the main difference from unit testing and this proof harness. But the following things are pretty much very familiar to the developer. They are writing in C, in this case, saving the previous state of the data structure. For those of you who wrote proofs before, this is like history variables, where we wanted to capture the state before the operation. Then we call the operation under verification. In this case, this s20 stuffer resize if empty function. And once we call the operation, we are injecting the non-deterministic values here to explore all possible paths in this execution. And then lastly, we check post conditions, very similar to unit tests again. Of course, these tests is a shrink version of the real one because we can add as many post conditions as possible, right? And I wanted to remember, when I showed you before, here, there are even extra post conditions that we can embed it into the code, and we don't need to recheck them into the harness. Or it depends on the developer where they wanted to place them. Okay, so writing unit tests like proofs. The final thing I just wanted to remember to emphasize, rather than writing one single proof for a piece of software and let it be, it is extremely important that we integrate that into continuous integration. And we check those properties on every code chain so they can remain true. Okay, so now we came up with the methodology, we apply over several projects. What are the biggest challenges that we are facing today? And that hopefully the community can help us improving them. The first thing that we have in mind is soundness. Whenever we wanted to prove a property over a program, we cannot have flaw assumptions. We need to maintain soundness as the highest priority for us. Because once we claim that we have a proof over a certain property, we need to be able to sustain that claim with our assumptions. The first big challenge for us with this methodology is scalability. Everything that we do at AWS is deployed at a large, very large scale. One of our services, I believe S3 get objects, one of the API, it's called over 47 million times per second. So we need, whenever we think of a methodology, we need to think of one that can scale to more complex and hard systems. And in that case, we are investing in function contracts. We are developing function contracts to adopt a more compositional technique. And I'm going to talk a little bit more about how function contracts can help us scale this technique without compromising soundness, which is our first priority. The second thing that we are tackling right now, it's unbounded verification. As I said at the beginning, both tools that we are using today, CBMC and Kani, are bounded model checking. What does that mean? We need to, in order to explore all the state space, we have the state space explosion, and sometimes we needed to restrict the input of the system or restrict the number of bounds that we have over the loops of the program. And these can buy us adaptability, because it's fast, it's push-button approach. However, the differentiation factor of our community, of the formal methods community, is using mathematics to make universal statements. For all elements in this array, this property will be true. And that's the differentiation factor that we wanted to apply when doing work like this. Every software project that wants to adopt automated reasoning, they want something a bit stronger in their security assurance. And we can do that if we invest in those universal statements, okay? In order to do that, in our case, we are implementing support for loop contracts, loop invariants, decreases clauses, and so on, in order to eliminate the need of the bounded part of our approach. And another thing that is important for any person that has worked with software verification, coming up with loop invariants is a difficult task, right? You need an inductive loop invariant whenever you wanted to apply deductive verification techniques into your code. So imagine asking that from developers. So we need to think of approaches that can help us synthesize those type of specifications. So we are also investing in synthesis of inductive loop invariants to cross the boundary. The last one, which is a point that I wanted to emphasize more and more, we shall never compromise in soundness. We need to warn developers or whoever is writing those proofs the impact of their assumptions. Your property, your proof, will only be as strong as the assumptions that you make. The fewer that you make, the better. They needed to be audited, they needed to be documented, because if the assumption is flawed, the entire property will be flawed as well. More of that, our tools, and that is a claim for, it's a ask for the community, needs to provide the mechanism to check those assumptions. For example, as I mentioned, when we are checking, when we are writing the non-deterministic inputs, we can have preconditions, right? If a precondition turns out to be false, and we ended up assuming the precondition before checking the function, this leads to vacuity. Every single property that you will check after a false assumption will be invalidated. And sometimes some tools, they don't warn anything on it. So how can the developer or the proof writer imagine there is something flawed in the process? The last one is we need to make specifications as explicit as possible. As I said at the beginning, we are using the same language, C or Rust, to write our specification, our tests, right? But then there are a few constructs that inject implicit assumptions. For example, there was a time where we were calling the malloc function with numbers that will always be strictly positive, never zero. So we were restricting our state space. This was only done in code, but then we were missing a part of the state space that we wanted to explore. This was an implicit assumption because they were just writing code. It wasn't like an assumed statement in a proof. How can we make sure that those implicit assumptions can be extremely obvious and documented to developers? And our tools should be the ones to help indicate that. Okay? Now, though that I explained the methodology that we have created and adopted so far across many projects, I've explained one of the difficult challenges that we have right now. I wanted to show you a case of what we have done so far to come as close as possible to improve those challenges, meet them. So the first thing that we did is we implemented in CBMC a function contract system, a way to do compositional verification. And we were doing that because whenever we were tackling a code base, if you have a function, you can start at the very bottom layer of this code base on functions that do not have any dependency. As you were proving functions and functions, you go higher into the software stack. Question, how can we reuse the proofs that we did for the bottom layer to high-level functions in this code base? Most importantly, how can we soundly use abstractions in this process? When we wanted to be as close as possible to the developer workflow, right? So whenever developers are doing testing, one thing that is really familiar to them when we are talking about abstractions is stubbing, right? You can write a mock, a piece of code to replace complex parts of your functions. However, when we are dealing with proofs, how can we make sure that when a developer writes an abstraction, a stub, for a complex part of the function, they are replacing that with an over approximation of the original code? We were discussing about that a few days before. If you do not replace the original code with a sound over approximation of those operations, you are limiting the state space that you wanted to explore, and your proof can have a flaw. You can miss a bug, you have a soundness problem. So we need mechanisms to ensure that that won't happen. We are investing in function contracts because the same specification that you use to prove that a function holds a set of property, that the function is memory safe, for instance, you are going to use the same artifact later to soundly abstract, to create an over approximation of that function. And those abstractions will help us scale to even further up in the software chain. Our function contract system contains the usual building blocks of a function contract system. Requires clause, where you define all of your preconditions. Ensures clause, where you define all of the postconditions. And we have assigns clause, where you define the right set of a function. Assigns clause will define all of the memory regions outside of the function scope that can change, the global states. That is really important, because if the global state changes, it can affect other functions besides the one that we are verifying at this point. And there is another thing that we always keep in mind, the burden on the developer for writing specifications. So our contracts are opt-in. If anybody here has worked before with tools like Daphne or Crusoe, where you need to write specifications for your code, you know that for every single function in your call graph, you need to write function contracts for all of them, because the tool relies on those specifications to create the proof. For us, you can write function contracts for only the functions that you want to abstract later, because the verifier has the option to use the original code. And then some people can ask, for verification, using the specification is way better. It can be way faster instead of using the original code. Why would you want that? In a lot of cases, verifying the code itself, it's not as hard as writing the specification. It takes a lot of time. And the currency that we are trying to save here is the engineer time of writing those specifications. The maintenance from maintaining those specifications later. So the approach that we wanted to use is you write a function contract for the function that you wanted to verify, and you write function contracts for all the complex functions in between that you wanted to abstract later, so you can have sound abstractions. Here, I have a very simple schema to show you how the contracts work in actual code. We have this function foo, has 2 parameters. We have a requires clause with a set of preconditions. We have our assigns clause, where we can define global variables or all of the pointers that might point to memory regions outside of the function, of course, that can change, and our ensures clause. This is for checking that a contract is correct. It's checking that the implementation of foo respects this contract. Later on, we are going to use the same set as a sound abstraction as this call to foo right here. We have int z equals to foo will become in our code assert r because we wanted to assert all of the preconditions, havoc a because all of the memory region that might change, that could be modified by this function, needed to be completely havoked with non-deterministic values, because we don't know which operations could change that in that way. This is the part of doing the over-approximation. Then, of course, the return of the function will also be havok with non-deterministic values, and we assume E, the set of postconditions. These assumptions, they are designed to restrict to properties that we have proved before, these havok values, okay? And this is done automatically by the verifier. So we know that we are operating over a valid abstraction of the function foo. This is the first part to help us to tackle scalability without compromising soundness. The second part is the part that helps us tackle bounded verification. Here, so by default, CBMC unwinds the loop and inlines the function calls. The analysis is completely bounded. So there is a lot of code repetition. If I have a loop over that has an upper bound limit of 10, I'm going to replicate this code 10 times, all right? And then I will perform the symbolic execution on it. The way that we are doing here, we are using loop contracts, which are a combination of loop invariants, decreases clauses, which I don't show in this slide. Decreases clauses help us to prove termination of the loop. I'm not going to go too deep into detail, but we use that across other projects as well. I just don't want it to confuse that much. And assigns clause, which is the same way. The loop has a context, and we needed to define all of the memory regions outside of the loop that might change, right? This is super important. I'm not going to go over too much these transformations that we do, but here we have an example of a normal loop. We have this assume P is just all of the properties that should be true before our loop. We have the initiation, the guard, the update, the loop invariant, the assigns clause. I removed the decreases clauses here, meaning that we are not proving termination for this loop, and we have the body S. This loop will be transformed into this Hoare-style reasoning, where we have the initiation, we assert the invariant because they needed to be checked right before the loop. We havoked all of the right set in the same way that we did before because we needed to start from a completely arbitrary state. We assumed the invariant because we needed to assume the restriction should be true across all the loop. The loop now becomes an if statement where we reuse the guard, the body, the update. We check for inductiveness because we needed to check the invariant throughout the loop body as well. This assume false is something completely specific to the symbolic execution, so we don't continue in this path and assert this again when we go through the body. And at the end, we satisfy the assertion right after the loop, okay? This has no change on the usual literature of applying a Hoare-style transformation using loop invariants. But this...
What's G? Is it guard?
Oh, yeah, I'm sorry. G is guard, yeah. because after the loop it needs to be false. Yeah, exactly. But this helps. So there is one detail here that I wanted to call attention for everybody. When we are doing the default methodology, this loop would replicate the code for any times that we wanted to unroll this loop. Now we only have an if statement, no more code duplication. And we are proving for all possible values in this loop. Okay, so now let's see that new approach more in action. At the beginning I showed the methodology on S2N using a normal bounded way, right? The usual way that we do. Now I wanted to show an example with FreeRTOS. So as I mentioned before, FreeRTOS is this leading real-time operation system. It is downloaded every 170 seconds, so it's quite popular. And among those libraries in FreeRTOS, there is one called core.json, which is a JSON parser, right? All implemented in C. What we did is we took all API level functions. When I say API level functions, I mean the functions that are handled to the users, right? The core.json have 4 API level functions. And we were able to prove that all of them are memory safety for an unbounded buffer. For this particular library, this is really important because the buffer, the input, comes from outside. It's untrusted data. And usually, if you see the list of software weakness, a wrong input validation in parsers, such as core.json, is one of the open doors for attackers, right? So making sure that the system is memory safe, since the data is untrusted, is important to avoid even security liabilities. So how do we do that? This is the call graph of one of the API level functions, JSON validate, okay? Usually, in our standard approach, what we do is to write this unit test style for JSON validates, setting up the non-deterministic inputs, calling JSON validate, checking post conditions, right? In this particular case now, we wanted to write a function contract for JSON validate, so we can make the specification as clear as possible. The function contracts that we are writing in CBMC uses the same idea as we said before. The specification should be in C, the same language that the developers are using, okay? This is the simple specification for JSON validates. We have a requires clause to list the preconditions, and we have an ensures clause to list the post conditions. There is no assigns clause here because JSON validates only validates this buffer. It doesn't change anything. So there is no memory region outside of this function that will be updated, not even global variables, okay? These preconditions and these JSON validates are predicates written in C that the developers can understand, right? This is important for adoption. The second part is now, if we do the usual approach, this would not scale. And one of the reasons why this would not scale is that if you take a look at the call graph, all these functions contain loops. If we do the usual bounded model checking approach, we needed to enroll all of these loops. And every time that we enroll, we duplicate the code for all of them. So the state space is growing as we increase our bound, right? This is unfeasible. Or we needed to maintain a very limited bound to tackle this function, okay? What we wanted to do now is to write loop invariants to replace with the transformation that I showed you before. So this, for example, one of the functions is skip string. And in this function, we have this while loop over here. And we annotated this loop with an assigns clause. This I is declared outside of the scope of the loop. So it's a memory region outside of the loop that might be updated within the loop context. We have the loop invariant, which must be inductive. So this transformation is valid. And we have the decreases clauses, which I don't want to go too much into details, but it needs to monotonically decreases in order to prove termination. Okay? Once we have annotated the loop with these 3 artifacts, we are able to prove properties over these with unbounded guarantees, and we are able to prove termination of this loop. All loops in core JSON were annotated with a decreases clause and a loop invariant. So all of them are proved with unbounded guarantees and for termination. Here, I wanted to claim another thing that I said about the challenge, and I hope the community can help us even more. Asking developers to come up with such specifications is a hard task. So we need to come up with techniques to help them come up with those specifications, right? It's not only a loop invariant will not only be a property that needs to be true across the entire loop. The property true is true across all the loop. Please help us on that. Okay, then if you are using any standard technique, as I mentioned definite before, which is an amazing tool that I love, you would need to write function contracts for all functions in this call graph. But in our technique, the function contracts are opt-in. So what we do is that we look at the call graph and see which parts of this code base are complex enough. Where can we decompose the problem into smaller parts, divide and conquer? We notice that any scalar has a lot of loops in it, so we can probably tackle the verification of that part and use an abstraction to replace all of those operations if we have a contract for skip and scalar, okay? So instead of writing a contract for all functions, we are going to write one for skip and scalar. The same for skip collection, which is the very beginning. Instead of writing a contract for all functions, we wanted to tackle that. Here, there is a caveat, though. It is really nice that we don't have to write all of those specifications, and that we are able to focus on the parts that are complex for verification. But how can a developer know which parts of this code graph are complex for verification without any tooling? That is hard. People that have experience proving code, they know a few things that can be complex. As I mentioned before, loops are complex, so this is an indicator for us by looking at the code. There is another thing, if you're working with SAT solvers, if you have arithmetic operations over non-deterministic values, you have basically an undecidable problem, so that is very complex. But we need to come up with ways that our tools can tell the developers which parts of this code base is complex for our proofs. So they can, so the tool can help them to write a specification for those spots, right? Seeing, like finding those hard tasks is also difficult. But okay, once we are able to write the function contracts for those functions, we are able to verify this entire call graph full of loops in 65 seconds. This is unbounded, I wanted to emphasize that because I think this is really cool. Unbounded guarantees for this core JSON parser on 65 seconds. I believe this is quite impressive. And this is the collection of proofs that we did for FreeRTOS core JSON. This HTML report is the report that we emit in CI, telling them the first three functions are the API level functions, which start with JSON, and all of the other functions, it's 14, I believe. This 15 total is counting one more. All of those are complex functions that we wanted to abstract later on. And remember, we prove that those functions are memory safe and use the same artifact, function contracts, as sound abstractions layer. Here I wanted to show something. The numbers might be quite small, but I will show it to you. We proved the same code base with our default approach, CBMC with bounded proofs. And it was taking almost 2,500 seconds to verify all functions. Interesting enough, this is using abstractions as well. Without abstraction, it wouldn't finish. These abstractions was stubbing, not checkable abstractions, right? When we started to using function contracts, but we still with bounded guarantees, no loop contracts, the time it was still 2,500. It was still quite hard to prove all functions in this code base. Now, when we apply bounded guarantees, the time dropped to 70 seconds, from 2,500 to 70 seconds. That's how long it takes in CI to prove this entire code base with unbounded guarantees. And one of the factors that caused this massive drop is because there are no more code duplication, right? All the loops now are being replaced with this transformation. Other thing, we are reusing the code, right? We are using the function contracts as abstractions. We need to be careful. Because we are using over approximations, it's not always that we have these performance jumps. But it's nice to see that it's possible here. This is something more interesting. At the beginning, when we are using a standard approach, we needed 25 gigabytes of RAM, right, to run all the proofs. That's cost in memory. When we were using function contracts, these went to 40 gigabytes of RAM. This is because when we see this style of assume guarantee proofs and decomposition in software verification, we may think that is quite easy to do, right? You have assertions, assumes, you invert it, it's simple. But checking a signs clause, checking the memory regions that might be modified across every single operation can be very costly. And we annotated the code. We are using an approach called dynamic frames to track all of those memory regions and make sure that we get the correct right set of the function. And when you combine that with code duplication, try to unroll the loops, you need a lot of memory because of those extra annotations. But now, with unbounded guarantees, there are no more code duplication, right? We perform a transformation in the loop. So then we are able to drop to 3.5 gigabytes. Why am I saying those things? Because now we are able to have these costs in CI. If you wanted to use Connie, for example, our Rust verifier, you can go to GitHub Marketplace and use it for free in your CI. And if you can use proofs that falls into the same cost, you can run your GitHub action in a few seconds to check properties over your code, right? So this is impressive because this is removing a huge barrier for adoption for developers. I talked a lot about C verification, right? We have done a lot with CBMC over the last few years, but all of the same techniques we are applying to Rust. At AWS right now, there is a huge movement to write more and more Rust code to build systems. We wanted to take advantage of the guarantees that we have from the Rust type systems and focus our proofs and functional properties, focus our proofs in the absence of panics, and so on. It's not always that this is the case, but here we also have I'm sorry if the code has extra stuff, but you can see that we have the same requires and ensures clause to prove this little function, which has a loop in it, and later on would be used as a sound abstraction. Okay, so the same things that I talk over C would be applied to Rust as well. This is being used in production in Firecracker as well, in this micro VM manager. Okay, so I always wanted to close with a few takeaways. If you walk out today from this talk, there are two things that I wanted you to keep in mind. The first one is to push towards unbounded verification. The differentiation factor of our community is to be able to use mathematics to claim, to reason about infinity numbers, to have these powerful claims that really differentiate us from testing, right? And there should be a balance between adoption and making those bold claims. The second one is the scalability without compromising soundness. There is a lot of techniques that we can use as abstractions, but soundness is really important, and that's why we're investing on those compositional techniques, function contracts for proof decomposition. And most importantly, we need to convey to non-experts the impact of our assumptions, document them as clear, as explicit as possible, because if they are flawed, all of the properties are doomed. And last, how can I say that? I love competitions. The SBCom competition is great. The SAT competition is great. It really helped our community to further the development of our tools. But how amazing would be if we can apply our tools to real code in the wild. All of those projects, and even if you don't want to work on these projects, there are many other out there, but all of those projects have proof artifacts written in the same language as the code that you wanted to verify, which makes easier for other verification tools to adopt. So if you have a C verifier, you can apply them on those as well. The constructs that we use in CBMC and Kani can be replaced for your own verifier built-ins. So even though competitions are great, I urge you to also attempt to apply your code into those real projects, right? Because there are times that we wanted to adopt some of the methodologies, do comparisons, and we ended up being stuck in small problems around technicalities, you know, like something that doesn't compile or, I don't know, small things, you know, because our tool should not be framed into a competition. It should be applied to real code. Thank you so much. Again, thank you so much for coming here on a holiday. And the last thing that I wanted to say is PhD students, if you have PhD students, master's degree students, we have internship available across the US, New York, Minnesota, California, Boston, you name it, Seattle. So please take a look, talk to me. This is my email. Thank you very much.
Okay, thank you for the talk. We have time for some questions.
Thank you. It was a very, very interesting talk. I have perhaps way too many questions, so I'll start slowly. I like this work. It reminds me of a previous lifetime of my work, right? In many, many ways. And let me ask the first questions. Uh, yes, there has been a very long discussion on how to specify your properties, right? And usually the temporal logic people or other kind of people will say, well, this is a very short sentence, and once you learn it, it becomes easy, which is true. But there is the once you learn it part, right? Now you put it into your code, but you know, it's kind of contradictory because you say that it's in code, right? But when I read it, I realize it's harder than it looks. I mean, writing those things is not that simple. And the examples you've shown that you verified, you actually got the code ready and had to insert the specifications, right? So my question is, have developers adopted, accepted it? Are they proficient in writing these specifications? Because I think that would be a challenge as well. I would like to know how you deal with that.
That is actually a great question. When you say proficiency, I tremble a little bit, right? Like, because not all of developers would be proficient in writing such specifications. I cannot emphasize enough of telling a developer that they could write the specification using the same language is a game changer, because they are already willing to try it, right? It's like you are going to write code in the same language. Nothing changes. It is true that some concepts are different and they needed to wrap their mind around it. For example, how do I set up non-deterministic inputs, right? This mindset that you are going to explore all possible behaviors once you set up an integer that can have any value is different from a developer perspective. But once they learn that, the rest of the things becomes a bit more easier to understand. To me, as we observe it so far, of course, there is a bump to learn some of those things. The bump is way lower than for other types of specifications. But the biggest problem is debugging. Because once they write those unit-like tests, or even the function contracts using the same language, they might run into problems, right? But then is when things become very different, because you are not debugging a compiler. You are debugging a verification tool. You are not executing your code. You are going through symbolic execution, encoding this into a set formula, and you needed to understand the implications of what you wrote to set. That's difficult to convey to a developer. That's when we need, like...
It took me 6 months to understand that.
Yeah. That's the difficult part, right? So a developer will, like, my code is so simple. Why it's not working? It's stuck into the verifier, right? And then they are performing multiplications with the U64-bit integers that are completely non-deterministic. And I'm saying, like, this problem will never finish, right? But how do they know that? You know, it's sat, you know. So this is the difficult part. In Kani, for example, we wanted to address many of the UX problems that we are having. That's why I really claim, like, let's try out our tools in real code so we can feel those same pains, right? So for example, whenever they have a counter example, we have a feature that called concrete playback, where we generate a unit test with concrete values so they can take this test and debug the problem in a debugger for Rust, right? This is really nice. This doesn't solve problems when they are dealing with complexity things on the verifier, but it can help them address any issues that might come from their code. So it's like, it's a long answer, but the short of it is I don't think writing the specification is that big deal because writing the same language helped them a lot. But debugging, it's the real challenge. And the second thing that I would say to that is that expressiveness, what you are willing to write, depends on the property that you wanted to prove. I always ask the developers, what matters to you in this code base? Is it memory safe alone? Okay. It is functional property because the more you wanted to prove, the more you needed to write. And the more expressiveness, you needed to be more expressive, you know? And we needed to go into logic, yeah.
Okay, I had an experience that was very interesting, perhaps it might help you. We were tasked, I was working at Intel, and we were tasked with modeling and verifying this piece of code, this hardware piece of code, and the developers were supposed to help us, and they didn't want to. So we asked them for, let's meet and discuss this, and it's maybe 3 days or so. But eventually we got it, we modeled it, and the first time we came up with unexpected results, we got their attention.
Yes.
Right, so from this point on, every time we call them, they answer.
Yes,
right?
yes.
So this is an interesting thing. If you show your developers, look, see, you found this bug faster than you would have otherwise, right? Then he or she will, be enthusiastic about it.
Yes, exactly. It is very interesting that you say that because we report that in the paper. Because like the best way to talk to developers in our paper was like never set up a meeting. They would hate that, right? But send a pull request, with the bug and the fix at the beginning to show value. Or send something that will break their code. But a pull request is the best communication channel to actually talk to the developer. It will grab their attention better than any message at all. You're right. There is a graph in this paper where we show, as we were writing more proofs, the things that we are uncovering, and then we grab the attention of them. But as I said at the beginning of the talk, one thing that is really nice across AWS, I believe the automated reasoning group is the largest group in formal methods in history so far, even larger than the one in Intel right now, because they are really buying our techniques. There is a lot of value on applying those mathematical techniques to those systems. I remember even when they were writing those predicates, like I showed at the beginning, like this data structure, what is true about that? They were realizing, oh, I thought I have come up with a data structure that will look like this. And then they try to write the specification and it wasn't the case. And they were like, oh, this is actually helpful. Yeah.
Oh, yeah, it's a very interesting feeling when you actually find something that's completely unexpected. Right?
Yeah.
So can I ask one next question? Perhaps I should wait for other people to ask questions. Do you have any more questions?
No smart pointers.
For the talk, it was very refreshing, especially because I also, when I started applying in verifier mostly code, I had some of the same trouble. At the end, you mentioned that trouble of applying other verifiers. Uh, I would say that this is partially fault and not completeness of the takas as well, because most of verifiers, right now that I know of, we all focus on implementing those functions, so the SBMF. But as soon as we start applying real code, you notice that they are not enough. You need more expressiveness, you need to optimize bits of code. And by what I noticed in your talk also said that you also create new intrinsic functions for CBMC.
Yes.
And now I'm asking your opinion. Do you think that there will be a way of us having a more appropriate API for how software verifiers should have?
Yeah, that is interesting. One of the problems of our community that we discuss, any person that has participated of TACA's SVComp is about standardization, right? Like there is no unified way that you can define all of the predicates because it really depends what you're trying to prove over the software. What I would say is that once you try, so two things. Number one, to get some sort of standardization, we needed to get together as a community, right? And the competitions kind of help with that, but the problems are limited. The thing that I would envision is that the competitions, I think there is one called Verify This, which gets some real code, but incorporating this type of real code into the competition so we can work together, to come up with that, it might be a way of doing that. This is for standards, to collect the types of predicates that we need that all verifiers should handle. The second thing is once you start verifying, you will feel the pain and you will feel the need, It's like to come up with such a thing. For example, everything that we're encoding to SAT. Why we are not using SMT? If you have a tool that can model check with SMT backend, we should try it, right? Because there are other theories that could help us on those problems. When we are discussing with the memory layout, I told about when I was discussing about function contracts, coming up of a way to track the memory regions quite difficult. Tools like Daphne use SMT backend. Is there any way that we can use bit vector theory? Maybe not, but array theory or something like that to help us in that sense? I don't know. You'll be very interested. And everything is open source, it's for free. You can use it.
Since you mentioned the contracts, I'm also curious because, as you mentioned, this is focused on CI, right?
Yeah.
And I expect the CI to run on every commit.
Yeah.
And some commits might change functions that are not related. So are you re-verifying every contract, even though the function was not changed? You cache it somehow?
That's a good question. Yeah, we re-verify everything. And this is a bit dumb, right? We could come up with a better approach to only verify things that have changed in this code base, right? We need some sort of equivalence checking in that sense, which is can do more harm than good because it can be expensive as well. But yes, we re-verify everything. Yeah.
Okay, I'm sorry, I'm going to have to cut the question short. We're going to have a workshop right now. Come back here at 10:30. Let's take our speaker again.
Thank you.
We'll see you where there's a minus sign in the shares. It means that the founders lost 100 shares because they transferred to these guys. Okay. And the cap table itself is a snapshot of the system. So if we accumulate those transfers, we end up with a table like this. And this table, it's like the transactions are transitions and the table is the state to get more closer to computer terms. What we need to do is to validate that the transitions respect what domain experts understand as correct properties of cap table. And what can go wrong with cap tables? Because if it always worked so well, we wouldn't have a problem. They are maintaining spreadsheets, and we saw like 10 rows of transactions in this example. It can be 10,000 rows. It can be very unwieldy. And everything is maintained in spreadsheets. Also because different investments might feature different rules, such as this investor wants to treat exchange rates as if they were always the value they were in last year, so he doesn't have risk in the exchange rate. So they can get it idiosyncratic. And Excel spreadsheets can handle any kind of business rules, right? But they are very error prone. They are time consuming because to build the spreadsheet, you need to read hundreds of pages of legal contracts that essentially say a figure, you know, but it's like hundreds of pages of lawyer text. And there's no interoperability. So this is the main problem, because let's think about a startup. It's raising money from 4 different funds, and they need to know who owns what in the company to know if the transactions aren't transferring wealth between investors inadvertently. And mistakes are bad because if you consider a company that's worth several $billion and you have a 1% mistake, there's a lot of money that is in the wrong hands. So this leads to litigations. There's many law firms that are specialized in startup transactions because of this. So we would guess that there should be an industry standard for this. And the Open Cap Table Coalition was formed 2 years ago. It has 60 companies in the industry, including investors and law firms. And they set out to devise a standard so they could exchange data for startups during negotiations. But they chose to write the format in JSON schema. So JSON schema is a small technology that can validate JSON documents. But the only thing that JSON schema can validate are types of properties and the presence of certain keys. And when I mean types, I mean very simple types, not dependent types. Like is it an integer, a string, or a Boolean, and maybe a range of numbers they can validate as well. And the key idea in the format is that entities like securities and companies and investors are part of the model, and transactions are the other part, that we change the securities. The standard is packed with business knowledge. It's a large format. It can cover very different types of investments, and it's very rich. But the choice of JSON technology makes it very hard for anyone to describe the invariant of the domain. So, for example, one very immediate invariant is that there can never be a negative number of shares in the world, right? Because you issue a share, then you can cancel it, but you can't go below 0. And you just can't check that in JSON. So it brings the question, what is a format worth if you can't validate data on it, right? And the coalition knows it's a problem for them, that they can't specify the business rules that are required to validate the data. And I chose to use Alloy to model a fragment of the domain, but it turned out to be a new model that is significantly different from the original. And in a model, I'd like to capture the notions of a security, an investor, and issuances of new securities, cancellations, and transfers. So for those who have had no contact with Alloy, it's a formal modeling language, or more precisely a methodology, because it comes with an analyzer and an interface to use it. And a model in Alloy is built from relations and constraints. And the language for constraints can be used to state properties. If you don't enforce a constraint, it becomes a property that you can check. And the properties are translated to a set solver, which checks the properties and can verify. So it's a form of bounded model checking as well. And Alloy has a very friendly syntax. It resembles OOP, like it resembles JavaScript, Java, but it always feels like writing a schema in SQL, which is very familiar to developers, right? Because one key point in this work is that we are interacting with an industry coalition, so they're not computer scientists. So I think that the same idea that Felipe brought, that verification must be approachable to developers, appear here as well. We need something that is very easy to pick up. So in our model, we followed the original ideas. We have securities that are transferred between people, or issued or canceled, and transactions. And what are properties of the model that we would like it to have? Coming back to the domain expertise from finance. It must be accountable or traceable. So whenever someone owns part of a company, I want to be able to see if they own it because it is an issuance or a transfer. And since securities can be transferred over many investors, this tree of transactions can grow quite long. You need to be sound from the accounting perspective, so money cannot disappear or be created out of nothing, except on issuance. And it needs to be easy to use. And there's a point in the proposed model from the coalition. It is based on event sourcing. So they model the events that happen in the system, but you have to play back all events to get to the current state. Since they don't have the business rules for updating the states, they can't compute the current state. In our model, it's very easy. I'll show why, but it's very easy to compute the current state of the system. So this is what a security looks like. And it's one of the two key parts of the model. Security was created by a transaction, right? And so we say there's a signature with like a class or a table, and it was created by one transaction. So we have a nice control of cardinalities in Alloy. If it was canceled, it will have a terminal transaction, or if it was transferred, it will also have a terminal transaction. And it has a parent security. I'll explain why later. It has an owner, an ID, and Alloy can enforce an ordering over IDs, which will be very useful later on, and a number of shares, right? There's something in the model which is we don't actually transfer security. So if I have a certificate that says I own 100 shares in Microsoft, if I transfer it to my professor Anna, then I destroy my certificate and I create a new one for her in my model. So every security lives between two transactions, which is very similar to how many cryptocurrencies blockchains work. And the transaction side looks like this. So a transaction can issue, cancel, or transfer a certificate. So we have three fields: the input, output, and balance in a transfer. At issuance, it has only an output. It creates a security and stops there. A cancellation will consume a security. This input security will be marked as dead by having a terminal transaction. If the cancellation is partial, we must create a new security for the original owner with the remaining number of shares. So that's why you have balance fields. In the case of a transfer, we have an input security, which is consumed, an output security which is transferred to the new owner, and we have a balance security if the transfer was partial. If I have 100 shares, I transfer 90, the remaining shares are issued back to me as a new certificate. And this is what looks really like Bitcoin. And it's very different from the original model. And what is interesting in the model is that we can place the logic locally in the transaction. So we will use local constraints, and then we will check global properties. And this eases the reasoning. On the other hand, I'll go to the code, but by having it locally, it's much easier for the developer to read and understand what's going on, because all the logic is here. There's no other properties or facts lying around in the code to make things work. So how does an issuance work, for example, in terms of the model? So it's a transaction, and it has two additional fields because Alloy supports inheritance. So it's issued to someone, and there's a number of shares issued, right? Remember, I said that an issuance has only an output but no balance and input. It's this line. So this security won't have inputs and balances, will have output. And since this is an issuance transaction, there's no previous security that was canceled or transferred in order to create this one. So there's no parent for the security. It's an issuance transaction, so there's no transaction that created a security that was used by this one. So there's no parent in the security, and I'll show a graph why these parent relationships matter. The initial transaction of this security would be if we look at this issuance, it has an output security, and its initial transaction is this transaction. This is needed to eliminate dangling references, so only one security can be issued by this transaction. This looks like assignment, but it's a constraint, so here's how we say that the security we are creating belongs to this owner and has so much shares. And this is an accounting constraint, so you can't issue 0 shares, it needs to be positive. And the model looks like this when viewed graphically, and this is where it starts to become more approachable to developers. So this is an event where we have an issuance. The issuance had as output the security. Now the issuance this security was transferred. So it's the input of a different transfer. And this makes the issuance transaction be the parent of this transfer. And the output from this transfer has as its parent the security that was transferred. Same goes for balance. So let's suppose a balance was created. It has as its parent the security that was created here. And when we cancel, the cancellation is canceling something that was created by a transfer, so it's a parent. And there's the input and balance link. So it's a bipartite graph of securities and transactions. And we can use this graph to solve the auditability and traceability problem, because we will always be able to trace a security back to where it started and transaction back to where it started as well. And I mentioned that the ID has an order enforced by Alloy, and we can use this order to say that whenever a security is parent of another security, it must follow the order of the IDs. And this avoids cycles in the graph of securities, because if you have an ordered ID on all securities, you cannot have a cycle in them, right? It would violate the ordering. Alloy has a graph module that can very succinctly check that this is a DAG. So we just import the model, and we say parent transaction forms a DAG, and parent security forms a DAG. So we're good now for auditability. This is the command that I ask Alloy to check the properties.
What is a DAG?
Directed acyclic graph. Okay. Because there are no cycles in the securities graph. Okay. Thank you. And this is when Alloy translates the problem of checking this property into a set problem, sends it to a set solver, and gets the result back, and translates the result in terms of the model. So what you get from the solver is not only satisfiable or unsatisfiable, but you can translate the solution SAT finds to instances in the model. And here is where I check that all securities originate ultimately from an issuance. There's a planned security here, it's just as arrow in the slide, the model should be just this part. How do we do this? Alloy has a transitive operator, so we can ask not what is the parent of a security, but what are all its parents in a lineage. And this is very useful to get the model right, because the security must be traceable to a single issue. It's a requirement of the model. And I also added a counting check. So I went to know how many shares were issued. So I look at all the transactions, I see if it has the field issued shares and sum it. And canceled shares, I look at all the cancellation transactions, I see the input shares and take it into account. And I can use these functions to check that the whole system, there's always less canceled share, less or equal to canceled shares than issued shares. And then issued shares are not negative, but this is a global property. But we managed to make it hold by stating local properties. And from the graph, after a bit of reasoning, we know that we can count the number of links, and for every security that was created as an issue, for every security that was created, there must be either an output or balance link. So if we start summing, this is the count operator. We can count relations to the graph as a checksum. This is harder to rate the domain, but it's a very fast check. And it catches a lot of wrong cases if you know that the graph is right and no references are missing, right? So what is also interesting about this work is that contracts are very hard to read, like legal prose contracts, but we managed to express how the startup financing model should work without using contracts. And what I've shown here would be like hundreds of pages of contracts and purchase agreements. It's very succinct now. It is also checkable, which is very good. You need to check contracts so you don't lose money or anything, or get arrested, you know. So I think there's an interesting path here to do further research on what some researchers say it's code normativity, so law as code, right? There's a lot of work being done in smart contracts, but there's also work outside smart contracts, like legal text for immigration laws, for accounting laws as well. There's Catalan, which is a language which works more like this, but wasn't very applicable to my case, because it's very geared at legislation text. And smart contracts look like this, but when they bring verification or capabilities, they usually are looking at programming bugs, like integer overflows, reentrancy bugs, but not at the concepts that are behind the business transactions. And I presented the thesis to the coalition, and I was very happy to see the feedback, which for me says that there's something useful here. The coalition has 60 members, and all of them contribute some kind of engineering effort. They are trying to work towards a validator, and they realize it has no rules, right? It's just formats. So they are experimenting with state machines. So presenting this to them was very good, because they realized there's not only state machines, but a whole tooling that can be used to improve the format. And during this technical session group, they explicitly acknowledge that they need a better model. They need something with rules to make the forward go on. So it's not a completely theoretical work, it's very applied, but it hit something because it was useful. And what we're doing here is this. We are taking the syntax from the format, which is a syntactic format because it's for JSON documents. We are adding semantics. We couldn't do that in JSON, but we could do that in Alloy. So it was this work. Thank you.
Thank you for your presentation. Are there any questions? Yes.
This is very interesting work. There is a lot of things going on to auditability, to be able to, at AWS, I mean, to be able to check like a document, as you said, like the spreadsheet, and make sure that we can produce something that is spotted for legislation. But then when we do this kind of work, there are two things that we always keep in mind. The first one, it wasn't clear to me, how do you consume the input? You have your alloy model,
Okay.
and then you have a JSON that you got from a translation of the spreadsheet to the JSON, simple. And then you inject the JSON into your alloy model.
Yeah, there are two answers. One is I didn't do it because it requires using the Alloy's Java API. So it was more work than I needed in the thesis. And then the point of my thesis was to provoke the coalition into adopting something else that we can put more work into it. In principle, we can use the Alloy Java API to feed the data in the model. I think that since the data might be too big for Ali to check it properly, so a different idea, which I started working the thesis, not here. If you look at the Alloy code, it's very similar to programming, right? But it's checked. So
you were dealing with acyclic graphs that can be huge.
Yeah.
And like when checking these properties, especially if you're encoding that into SAT, it might be very cumbersome.
Yes. So the approach would not be to translate the whole specification, the whole data to SAT. Would be to check that the model is right and then build a software based on the model. That would be the idea, to use it for the coalition. Would be on this way, not direct on the data. I want to validate the model that validates the data.
Yeah, it would be very interesting to see like a real large data, being go through.
I would love to see this model being worked with real data, and I'm working together with the coalition on the data validation team to try to push these ideas forward. I'll do it.
The first question was about complexity. The second one, like when you build those rules, did you do any proof that those rules can guarantee any legal guarantees, or you were relying on Alloy and the SAT formula that you get?
Yeah, while writing the model, I could do something that might be related to what you're asking. I could state two properties, and my question was, are they redundant? And I could check if one implies the other. So there is some level of meta checking that you can check the model itself in Alloy. But ultimately I rely on the assumptions, right? What I consider the assumptions that are good for the model. I didn't find a way. I couldn't find a way to verify the specification itself.
Yeah. Congratulations. That's a good question.
Thanks.
Thanks for the questions. Are there any other questions? Yes. It is possible to use this code to do auditability in public transactions in Brazilian state, for example?
If the system that records the transactions was built using these principles, it would be checkable. But you need the system to be built according to the model to be checkable. So you're talking about a little bit of an adversarial setting. So they have transactions and you want to validate them. In this case, the coalition would build the system according to the model. In your case, I don't think it's applicable. If you had a model of the system that holds the records, you could, in principle, derive conclusions that might help you in validating the data, in this sense.
The input must be in the right standard for the model.
The model can be used to construct software that will not accept invalid instances. I think that is the most precise statement. So if you build a software that only accepts idoneous transactions of public records, it would reject the transactions you are trying to detect. In this sense, it might be a way. Okay.
Any other questions? So let's thank the speaker again.
Thank you.
The Automata Tutor, which is an educational tool for teaching and learning automata theory.
And with our tool, we focus on beginner learners, students at undergraduate level who don't have any experience in theoretical computer science and automata theory so far. And the student interface of the tool is a mobile application offering two core components. The so-called sandbox, which is an editor for freely building automata and running simulations in terms of inputting strings. And the construction can work on a mobile device in a touch-based manner. And the second component is the tutorial, which consists of a set of predefined and pre-generated exercises on automata theory that the students can solve and submit via the application and receive immediate feedback. So far, our tool supports finite automata and regular languages, but we're also working on extensions to cover a broader range of automata. And the idea of the tool is not only to make it easier to learn automata theory for students, but also to improve teaching. And the tool offers an interface for instructors, and that allows to either manually or also automatically generate exercises in the context of automata theory. Exercises can also be used as assignments for which the students will receive marks, and the marking of assignments can be done automatically by the automa tutor. So that allows the instructor to keep track of the students' progress, their marks, and the overall performance of students in a class. And in the development, we focused on three core features, which were usability, generation, and feedback. In terms of usability, we wanted to make the interface for students as easy to use as possible, a simple touch-based interface where components like edit states and transitions get automatically arranged, such that the limited screen space on mobile devices such as tablets and phones is optimally used. Then secondly, generation features that allow to automatically generate exercises for the students, and also an automatic generation of counterexamples. Counterexamples indicate where an incorrect or partially correct submission by a student differs from a memo solution, and we will look at the details a bit later. And then finally, feedback features. Feedback happens textually, also visually in terms of simulations that can be shown on automata. And there's feedback for learners as well as for instructors. For learners, we have the counterexamples for incorrect solutions. There's a hint system, and also students get informed about their performance in solving exercises and assignments. And the instructor can use the tool in order to keep track of the students' grades and can also view overall performance statistics. And the motivation for the development of the tool was as follows. Automata theory is one of the core theories in theoretical computer science, and also a basis of several formal methods. For instance, model checking, where Büchi automata are used. And we are aware that there are a number of editors for constructing automata and running simulations, but we didn't find them very friendly to be used by beginner students in undergraduate classes. And also the existing editors like JFlap, they don't offer features for generating or grading exercises. Moreover, in several instances, automata theory at undergrad university level is taught based on pen and paper exercises, which only offer students like an abstract experience of automata. They're not really able then to run those machines, and that causes that students often find automata theory and formal topics in computing rather unpopular in comparison to practical computer science subjects such as that involve programming. And this is what we wanted to approach with our Automa tutor. The idea is with these interactive elements that the application offers, we can increase the students' interest in topics in computing, and also in terms of classes, improve students' understanding of automata theory and related fields. And we don't only want to improve learning automata theory, but also teaching by means of the automatization features that our tool offers. And this big picture here illustrates the vision of our approach. In the center, you see the logo of our tool. And we have on the left side the instructor who can use it to automatically generate questions that can be then solved by students on their mobile devices. Solutions can be submitted, and several forms of feedback is available in terms of hints, counterexamples, or the grades that the students receive. And also the instructor gets feedback in terms of the students' performance and grades from the tool. Okay, and now we'll look at the core features in a bit more detail. And based on some example screens from the application. In terms of the usability, as I mentioned, it's a touch-based interface, and there are two modes of the editor, one for constructing automata and the other one for constructing regular expressions. And the automata editor allows by a single tap on the screen to add a state, and if the mode is changed, then by two taps on the states to be connected via transitions. And moreover, there's then also for transitions like an input interface to add labels in terms of symbols from the underlying alphabet. And once constructed, input strings can be simulated, and the runs over the input strings will be visualized. And the editor for regular expressions consists of a specialized keyboard just restricted to the operators and symbols that are needed, plus some convenient keys such as undo, redo, and clear. And for the exercises, those editor interfaces are then combined with the question specifications that explain which exercises shall be solved. And here some types of the supported exercises are listed. One type is to convert a given automaton to a regular expression, for which we see an example screen here. So a simple automaton is given, and the student has to provide a regular expression with the same language as the automaton. Or other question types are construct an automaton to match with a given regular language or regular expression, or it can be the case that an automaton template is given, and then also only transition labels have to be added by the student to match with some regular language. Okay, those are some of the types that are supported by the application. And as I mentioned, a question of those types can be automatically generated. And I explain the procedure that we have implemented for that on this slide. So it is based on a random generation of regular expressions. And as input of the procedure, we have the underlying alphabet of symbols, and then some constraints in terms of the length of the regular expression to be generated can be added, as well as pattern constraints. And here's an example. We may wish to generate a regular expression for the given alphabet consisting of the symbols A, B, and C. And then pattern constraints that might be that some substring may be contained, or maybe at the beginning of the regular expression or at the end of the expression, and the substring shall be randomly generated and shall have a length of 3. So then one possible random regular expression matching with those requirements would be the following here. An expression A or B or C star concatenated with the partial string A, B, B. And then our tool can automatically translate such a generated regular expression into a corresponding finite automaton and be translated into a minimal representation as seen here. So that allows us to always kind of generate matching pairs of a regular expression and a corresponding automaton. And questions can be then derived in terms of providing the regular expression to the student, and to ask the student to build an equivalent automaton via the editor. And next we will look how such questions can then be automatically graded. By default, we use a 2-mark grading scheme, and the grading happens by comparing the language of some memo solution with the language of the solution provided by the student. If the language of the student solution intersected with the complement of the language of the memo solution is empty, that means every string accepted by the student solution is also accepted by the memo solution, and 1 mark is received for that. And the second case that is checked is if the language of the memo solution intersected with the complement of the language of the student solution is also empty, meaning every string accepted by the memo is also accepted by the student solution, and for this second mark would be received. So this is kind of like an approach related to automata-based model checking. In case where we would get a non-empty set here, meaning the student solution would be not fully correct, then every string that would be contained in one of those intersections would be basically a counterexample string that shows where the memo solution and the student solution differs. And besides the standard grading scheme, optionally, the instructor can also provide list of particular strings that are part of the accepted strings, and a list of strings that are part of the rejected strings by the memo solution. And then the student would receive 1 mark for each correctly rejected and each correctly accepted string. And as I indicated, the grading scheme can be also used to generate counterexamples in the cases where those intersection sets are not empty. And those counterexamples are part of the immediate feedback that the tool offers. If we have such a question where an automaton is given and the student has to provide a matching regular expression and the student solution is incorrect, then by submission, the tool will output a counterexample string and informs the student that the submitted solution, in this case, incorrectly rejects the string AA. Besides counterexamples, if a student is stuck, also like a hint system is available, and a hint will be some randomly generated string, and the student will be informed whether this string shall be accepted by the automaton or regular expression to be constructed or rejected. And in this case here, if a hint is requested, an example hint may be that the solution to be constructed must accept the string BA. Okay, and our goal is to use the developed application in our undergraduate theoretical computer science classes. Before we will do that next year, we experimentally evaluated our tool with a number of students. The participants were 45 students in the fourth year of computer science studies. They had some previous experiments in studying automata theory in their second year, so it was already a few years ago for them when they were taught the subject. And we divided the participants into two groups. The first group had to work on a set of exercises first that was provided on paper, and they just had like follow like a pen and paper approach to solve it. And then after completion, they were provided with an exercise set on the mobile application to be solved. And for the second group, it was vice versa. They started with solving exercises on the mobile application, and then secondly worked with pen and paper. And after the experimental session, we asked the students to report on their preferences and on general feedback. And as well, we checked their general performance in the exercises on pen and paper and by using the app. And the major outcomes were as follows. In terms of the preference, we had that 60% of the participants preferred to use the Automa tutor, versus 40% preferred the pen and paper exercises. And as preference reasons, the student mentioned on the Automa tutor, they appreciated the ability to edit the solution during the construction, the ability to receive feedback, and the general mobile accessibility. Whereas when students preferred the pen and paper approach, they typically mentioned that they liked the familiarity with the format, which was the same format that they used when they studied automata theory in their second year. And also they mentioned they liked the ease of drafting or sketching an automaton on scrap paper before submitting the final solution. In terms of the performance, the differences were a bit more significant. On the application, the students received on average 76% of the total possible score, whereas on pen and paper only 29% on average. And that was also because of the fact that for the pen and paper exercises there was no immediate feedback that was offered, but on the mobile application the students were allowed, or the students received the counter examples and could also request hints. And when we compared the two groups, the one starting with the tutor first and then using pen and paper, or vice versa, we had that there was no significant difference when it came to preference and performance. So it didn't really matter if a student started with one of the formats first in terms of the evaluation of the formats. Okay, and as I mentioned, from next year on, we will actually want to use the mobile application in our classes for teaching the subject theoretical computer science. And for this, we are currently extending it to support further types of automata, such as push-down automata and Turing machines. And the long-term objective is to turn the automata tutor into an interactive textbook for this subject. And further interesting topics of future work are integrating automata-based model checking into the application, and also introducing support for using a digital pen, such that automata can be defined in a handwriting manner and then automatically recognized by the app. We have a number of ongoing masters and one PhD project, but also further projects in the context of the tool are currently available. And if you wish to try out the application, it is a browser-based app. You can simply scan the QR code here, and it will open the automata tutor in your browser. And yes, you're welcome to try it out and also to ask questions about the tool.
Thank you very much. It's very cool. Any questions?
Thank you for your talk. In your experiment, you mentioned that you had 76% of the score for students that were using the app. But usually when they do studies on learning tools, they also try to measure knowledge retention, which means that how much of the subject do they learn and retain after using the platform. So are you planning to do that? For example, the fact that you have a 70% score in comparison to 29% on pen and paper, it could be, it's an indication of the hints, as you mentioned, and all of the try and do it again that you can do in the app, but those actually convey on the learning the subject. Are you planning to do any experiments further on that?
Yes, I mean, we want to perform further or long-term experiments next year when we actually teach the subject. And of course, we would assume, like, if the students working with pen and paper only on a long term, they would also receive feedback and learn from it, but it would require kind of like manual marking, and they would only receive it typically after 1 week. So we also, we want to kind of like reduce the marking and feedback cycle with our app.
Yeah, and also try to differ if the hints are cheating or actually helping you.
Well, I mean, the hints could be, of course, switched off when it in the mode when actually assignment should be solved via the app. But if it's just like voluntary exercises, then that could be on. Yeah.
Thank you.
Mm-hmm.
Other questions? So, a question about your next steps. You mentioned going beyond standard defined automata. Actually, do you support non-deterministic automata and epsilon transitions and things like this, or is it?
Non-deterministic automata, yes. Epsilon transitions we haven't integrated yet.
All right. I would have loved to have a tool like this when I taught computability with Turing machines. So you mentioned Turing machines as one of the next steps. However, you have difficulty there for checking equivalence between Turing machines. So automatic.
Well, I mean, we have to see which types of exercises could be supported, but of course, like maybe it could be a kind of like input-based, generated Turing machine, and automatically check which inputs would lead to termination, or which inputs lead to acceptance or rejecting state.
Machine. And it's pretty painful to write Turing machines on paper and great Turing machines written by students on paper.
Yes.
All right, great. Let's thank the speaker again.
Hello, I'm Rafael. This is about the new SBMC version where we changed our parser for C++ to use a Clang AST. This is a joint work between Konijan, Mikhail, Franz, myself, and Lucas. So this will be the agenda. I will start explaining a bit of the motivations about why we wanted to change this parser. I will review a bit of the SBMC architecture. I think this is the last time in the event. Then I will show it working. Then a bit of experiments that we executed. Then I'll describe a bit of the feature work and where you can obtain and install SBMC. So I started with the motivations. Memory safety issues remain a major source of secure vulnerabilities in C++. You can always check Microsoft's reports that over 70% of the vulnerabilities are related to memory. Formal verification of C++ is arguably harder than C because C is basically a subset of C++. And C++ contains STO, it contains polymorphism, inheritance. It makes the verification way challenging. SBMC reached its maturity with C++ on versions 2.1. At that point, we were able to verify C++ 0.3. by using a parser which was based on Flex and Bison, which was inherited from the original CBMC. This parser, however, is very hard to maintain nowadays, because not only because the way we change the code internally of how SBMC behaves, but also C++ changed a lot. So we cannot evolve it to support some C++ 11 features, and we are completely unable to cope with recursive templates. So since we do not want to be a compiler in SBMC, we decided to leverage this task to a proper compiler. So by using the Clang AST, we then generate the go-to representation of that SBMC uses. So just to review a bit of how SBMC architecture works. So right now, the idea is we have, by having an input, a C++ input program, we generate the AST of the program using Clang. From there, we generate the go-to program. This go-to program is the one where we do our analysis. We apply symbolic execution. Then generate an asymmetry formula. This asymmetry formula is what we will check for safety or find a counterexample for a violation. This Clang AST has many other advantages, especially because the extra information that it contains allow us to create it easier for us to create the virtual table to handle the polymorphism. And it also solves for us the issue of recursive templates. It tells us exactly what we should have. Next slide. So, showing a bit of it in action. So we have a basic example for polymorphism. Have the class bird, which contains a public virtual method, which is the doit. and it should return 21. Then it have an inheritance of it with the class penguin, which contains the method, overrides the method doIt with for each. So the main is basically you create a pointer of bird and allocate a new penguin to it, and you assert that invoking the function doIt, you will return for each. This assertion should hold because the method is overrode. And initially, we start by producing the Clang AST of the program, which contains all the information about the struct and its constructors and inheritance. With this information at hand, we produce the virtual pointers and the virtual table. So here you see that the virtual, we have a virtual table for the bird class. We added a virtual pointer, which is the bird at bird. And it points to a virtual table, which contains the method to invoke the doIt from the bird class. And at the penguin, we have two virtual pointers, which can point to two distinct virtual tables. One with the thunk method, which will invoke the bird, the penguin doIt method. So when we finally convert it to the Go-to language, you can see that here at the top, top right, it's equivalent to the code, to the assert code. So we have the P invoking the bird at penguin and invokes the method doIt, which will have a dynamic dispatch to the thunk penguin doIt, which will finally invoke the correct penguin doIt function. So considering templates, this is the bug 10.158 for cBugzilla, which contain the nested template with non-type parameters. Now with this, for Clang AST, we're able to cope with this program. So the previous version, SBMC would just crash due to conversion errors. SBMC is aborted, and CPP check does not give any verification result. So here we can correctly identify what should be the correct value of the program. Okay. Yeah. So here you have the bit of evaluation. So we developed a few benchmarks and got a few other benchmarks. And comparing the pass rate of having the original front end of based on Bison flags versus having a Clang, we're able to cope with way more benchmarks. Now we're passing 100% of our test suite, and with less memory consumption and time. And now we can provide more accurate results faster. And we also did an evaluation based on many SMT solvers for our configuration. We found out that Bulector was the best. And that Bitvootlo, it's also come near the same results. So what was our future work? So the same as always, operational models are always needed. So we are going to focus on improving the operational models for all the C++ standard. We are trying to focus on having enough models to verify the OpenJDK Morel implementation, which does not contain shared pointers, but we should be able to cope with it. We also want to contribute with benchmarks for C++ verification, because right now, if you go any competition, for like the SPComp competition, we do not have C++ because of the lack of the benchmarks. And finally, how to download and install the SBMC. You can always go to our GitHub page, releases, and you can find it there. And here I have a few publications. So, yeah. Thank you. Any questions?
I think I'm monopolizing the questions, but I'll ask anyway. I think for the work, it's really nice to see that we're being way faster now with the new campaign. It's the project that was going on for a long time. It's nice to see them. You didn't mention some of the features that in the past was a differentiator for the SBMC. For example, are there any drawbacks in the support of exception handling? Are there any limitations with function pointers, the lambda operation, something like that? What are the key limitations with the Neo front end?
When you say limitations, it's not a new limitation. It's a matter of we're doing it still. So since the Clang AST gives us also the lambdas, which becomes a proper functions, it should be easier for us to implement it. The same as exceptions as well. We still have the AST of it, so it doesn't.
It doesn't imply on anything.
Yeah.
Okay. And the second question is about the operational models that SBMC used before. Now you have more libraries out there. And important, like when I mentioned before of using reliable abstractions, this is actually a big challenge because it's a huge piece of the standard library that is also in C++. And when SBMC wrote the operational models before, they never checked it against the original code. Do you guys have any plans on that, or just keeping writing the models as
It's still not the same, keep writing as we did before. Some of the original, oh, you want to?
Yeah, I was just going to say that we still have the operational models, but we cannot prove that they are correct. I mean, we can't, but it's just so big that we don't have the resources to do it right now. So one thing that we can do that we couldn't before is use the standard library to validate our operational model. We couldn't do that before because, well, because I mentioned that we wrote our own parser, so we had bugs and we couldn't like handle the standard library. But now that we can handle it, we can just use the standard library to validate our operational model.
Like conformance testing.
Yeah, so again, it's not a proof that it's a sound and complete implementation of the standard, but we can at least prove that we are as good as the standard implementation of the standard that is used by GCC and Clang. So that we can do that now. Not for all the standard library, there's stuff that we still don't support fully, like this, but at least we can do that.
That's great.
Any other questions?
I actually had one, which is, so SBMC can treat both C and C++, and for C++ you're using the Clang AST. At what point do those two front-end languages come to a common intermediate representation? I mean, at some point, it goes into SMT, so SMT would be the same backend for both, but is it within SBMC that you have an internal representation that you use both for C and C++?
At coach level, yes. No, it was actually the same. So. Okay,
so at what point do you kind of reduce the C++ features that you don't have in C? In the translation from the Clang AST to that intermediate representation that you have in common with C?
If I understood the question correctly, you mean like the specific features of C++ that C does not have an equivalent. Yeah. So our intermediate language has support for those features, like try catch, for instance. So they will cope with each other together. So with ultra-chess
Okay, so basically your intermediate representation actually
yes.
already supports natively the C++ features.
Yes.
It's just when you come from C, you're not using that. But,
yes, exactly.
Okay, cool.
One last question. You mentioned about the Mozilla bug. Have you applied the new front end with a real onboarding program?
Not fully. We're working to work for the OpenJDK from Morella. So.
Nice. Okay, if there are no other questions, then let's thank the speaker again.
Okay. Sure.
From prior knowledge when it's available. So here we have a neural network, typically a CNN trained on images, medical images, chest x-rays. And from this network, we extract knowledge, and I'll tell you a bit more about how this happens. But essentially, symbols are extracted in the form of a logic program in this case. But you can think of this as rules, and then they can be described in a traditional decision tree. And we need to associate some meaning to these symbols, ET, PA, and so on. So as part of a human-in-the-loop approach, an expert, a medical doctor, may identify, let's say, ET by going back to some of the images associated with that symbol, which comes from a kernel in the CNN, with, for instance, the enlargement of the heart, and associating some of the other symbols with an obscured diaphragm, implying a classification, plurifusion in this case. So the CNN is trained to classify the images. Through knowledge extraction, we hope to derive symbols and associated concepts so we can describe such rules. And also, an expert can inspect these rules and decide whether to keep them or remove them or keep some other rules that were not included, let's say, in the top 5, because here, when I tell you a bit more about the actual system, we are looking at one layer. In the case of CNNs, there is a natural candidate, which is the first fully connected layer. So we are not trying to explain the entire CNN, so that it's layer-wise. Each kernel is associated then with a symbol. We extract these rules, and we want a compact set of rules, not much point extracting thousands or millions of those. And so this is progressively done up to a point, and then it can continue. And we want to monitor the performance of these rules compared to the performance of the neural network over time. And so a user or a domain expert can inspect some of these rules and decide whether to keep or remove them, and then decide whether to add some of the other rules that are being produced. So this is this step here, we call it intervention. So now the decision tree changes. And this is happening at the symbolic level. And once we're happy with that decision tree, it can be added back into the network. And so this is the translation algorithm that I mentioned, which can also be done with the use of a teacher-student approach. So this is the distillation. We hope that this network becomes more compact, and you can see how now perhaps new data comes in, and the network that was not available before, the network can be trained further and the process can be repeated. So there are a few interesting checkpoints along this way, implementing the neurosymbolic cycle in a specific application here, in this case, medical imaging. Now, if we go knowledge first, so we have some prior knowledge or constraints that we want to add into the system. Let me go back to some of the early systems, K-band and the CILP system, where knowledge in the form of logical rules or logic programs can be added into the architecture of the neural network. So here in K-band, a hierarchy is created. So here you have neurons in a hierarchy derived with the weights of the network derived from the rules, A if B and C, B if D and E, and so on. Essentially the same rules as enlargement of the heart and obscure diaphragm implies pleural effusion. These rules being useful for the doctors also to communicate their findings. In the case of CILP, instead of a feed-forward network, we have a recurrent network, single hidden layer, and again, same process. You set weights and you define neurons based on the rules. And you also have a soundness guarantee, so guarantee of correctness of the translation from the rules to the network. Of course, if you then train it with backpropagation, that guarantee disappears. But there are some early results showing that if you have that soundness, then your performance after training with data may be improved, as you would expect, especially if the rules are correct in the first place. If the rules are wrong, then the network training would have to change those weights. So you hope that essentially, instead of starting from random weights and set of parameters, you have some prior knowledge to provide to the network. In the case of the CILP system, the negation here is negation as failure. So for those familiar with logic programming, this creates a non-monotonic system. So there is non-monotonicity in that a literal may be activated or fire or be true. The corresponding neuron is going to be activated, but then in later iterations, this may change. The truth value may change. So this is the idea of constraining the architecture in some of the early NESI systems. And if you take that to consider richer languages, for instance, modal logic, which has some interesting decidability results, then we can also do that over time by having ensembles of these networks. So if now each of these networks is one CILP network, and we can think of structuring them in terms of time points. Here we have agent 1 at time 1, at time 2, and at time 3. So we showed in this book that you can solve the typical muddy children problem in the neural network by having this kind of structure. So for those who are not familiar with it, children are playing on the playground. Some have mud on their forehead, others don't, they don't know, and a caretaker comes in and says, let's say at least 2 of you are muddy. Do you know whether you're muddy or not? So you observe the others. They're all truthful and intelligent. And so they reason about what the caretaker said at time 1. If they all say no, then they move to time 2, where now they have additional common knowledge that at least 2 of them are muddy. And if at that point they still don't know, they move to time 3 in the case of 3 children or 3 agents. And at that point, they should all know that they are all muddy. So this kind of reasoning over time, where knowledge becomes common knowledge becomes available, is possible with these structures, ensembles of CILP networks. Now, the holy grail, as it were, and the big question is, how about first-order logic? And we don't know really how to represent full first-order logic in neural networks, even the large transformers. But work continues in this direction, and work has been done since this realization that it's not an easy task to try and represent first-order logic. This is known as the propositional fixation of neural networks. The work has moved to try and represent such knowledge and use it in the loss function as part of training, as opposed to in the architecture. And the logic tensor networks framework is an example of that, where instead of adding knowledge to the structure of the network, we try to add that knowledge to the training, to the loss function. And then that can be first order, but it's essentially grounded in the network representation. So here, with the logic tensor networks framework, there is something called real logic, which is essentially first-order logic, many-valued first-order logic, where the constants are vectors. And you can think of some data points, and we may specify statements like this. So I have some data points. Some are A, some are B, so you can think of predicate A as a class, predicate B as another class. But then I can specify in first-order logic that if an element or object is in class A, then it's not in class B. And I can translate this into a mathematical constraint that goes into the training of the network. So here, instead of having soundness guarantees, instead of being able to prove that indeed the network is going to compute the fixed point, let's say, of the logic program, we don't have those results, and we try to measure reasoning capabilities. So how is reasoning happening as a result of incorporating such constraints into the loss function? Now, another interesting development from this line of work is the idea of querying the neural network. So the way that the network is structured is quite modular, or can be quite modular. And so if we try to now, having added such constraints into a neural network, and if we try to now think about how to do the opposite, go in the opposite direction, extract some knowledge from the network, then you can query it and try to see how, consider the idea of levels of satisfiability, because satisfiability in real logic is defined as learning. So this idea of not necessarily explaining an entire large system or explaining an entire layer, but querying and probing the network and getting some results which are levels of satisfiability of certain concepts. So I'll come back to this idea of querying the neural network. Just to say that there are other proof theory approaches also, and there's been quite an expansion of the research in this area. So other teams have been looking at reduction of logic into logical circuits and then using neural networks to compute semantics of those logic programs or logic statements more generally. The idea of soft unification also implemented in neural networks, and more recently SAT solving by neural networks, not just using the networks as heuristics, but truly translating statements in propositional logic into a neural network and running the network, performing inference in the network in a distributed way. I'll come back to that as well if we have more time. So we've come a long way from the time when neural networks were single hidden layer, like the ones I showed you for the CILP system, to now where instead of hundreds of parameters, we started to see millions and then billions and now, unfortunately, trillions of parameters in these networks. And one key question is the level of abstraction at which we may wish to derive such symbolic representations. So I mentioned the case of the CNN, where there is an input image, many layers of convolutions, and then a fully connected layer. So the process that I described, which is a collaboration with Fujitsu Research, is about looking at the kernels at this layer here and deriving a few rules associated with these kernels. So each literal, not CL and not PA, two kernels in here imply plurifusion, the classification output here. And then not CL and PA imply not plurifusion, this being a binary classification, so assumed to be a healthy X-ray. Of course, this can be extended to multi-class classification, and the idea is that I find it actually quite surprising that compact rules like these can be extracted from large networks like VGGs and ResNet. Of course, these are much smaller than the billions and the trillions of parameters that we were talking about, but still, in the case of images, it's interesting to see that the rules can be quite compact. There is a lot of redundancy in the networks, and there is a lot of explanation value in deriving these. Now, when we do that, we compare what is the performance of this rule set compared to the performance of the CNN. But more generally, we may have a complex network that we are happy to accept as a black box. So we may be happy to accept that a whole bunch of the object detection is left for the convolutional layers. And then there is a key layer which may look quite a bit like the CILP and the K-band and the LTN layer. So a layer that is placed on top. So taking this idea of modularity seriously and saying, well, at this point, I add something that needs to be explainable. I add a, let's say, hard constraint. Whatever is happening here at this point, I may want to satisfy some of these constraints, some of this knowledge that is being provided. Or it can be a soft constraint, and then, of course, learning can change things. So that's where I think this area of explainability is heading to. There has been an explosion of work in explainable AI, and I think there are some lessons to learn from that. In that originally we were hoping to explain or make sense or extract rules from entire neural networks. But as I said, we are now talking about 1 trillion parameters, and it wouldn't make any sense to have this kind of global explainability. It wouldn't make any practical sense. So you started to see approaches where people were looking for local explainability. So explaining just one input, explaining just one image, one X-ray, instead of the network as a whole. But that is also limited. And so what we are saying here with layer-wise global explanation is that we are not explaining the entire network because that's computationally intractable, but we're not doing local explanation either. These rules here are not just for this X-ray. They apply to the entire data set. So this idea of modularity becomes really relevant, I think. The other important thing that became clear in all the work in XAI is that measuring the utility of explanation is very expensive and application dependent. So it's costly, and there are, of course, different levels of explainability. You may need to provide explainability to different stakeholders. And there's been a lot of work in this space. But I just wanted to go back to the idea of fidelity, which was present all the way when neurosymbolic AI started, which is the idea of measuring the results obtained by the rules. So when you extract these rules, how is that performing compared to the network? Not so much compared to the data, but compared to the network. And this accuracy with respect to the network is known as fidelity. And whether we are doing global or local explanation, I think it's very important to have that metric before we go into expensive evaluations of which are more subjective and application specific. So again, when we extract these rules, we can check how good they are with respect to the network. And it's that metric, and we do need more of these metrics in machine learning. Accuracy is certainly not enough. We need energy efficiency, certainly, as one of the metrics. So I've been talking about mostly this idea of having more control, better control of the learning of these large models with some modularity, and then layer-wise global explanations of the important parts. For instance, you can think of the attention mechanism being very important. But with some well-defined measure of fidelity, how good is my explanation with respect to the behavior that I'm getting from the neural network? Right. So another application of these systems you can see here in this other paper, which was focused on LTN and explainability. You see the same idea of a cycle. There is background knowledge, there is data. It goes into a neural network, it doesn't matter too much what the network is, but if we can query it, then we would get satisfiability levels for certain concepts, and then make decisions about whether we need to go back and train the network further, provide more data, and provide more knowledge. In this example here, you have an illustration of LTN being applied where certain queries in first order logic now can be provided to the network. And this animal here, this extinct quagga, is classified as a zebra because it's not in the data. And so you have high satisfiability for that image classified as a zebra. And then the point I want to make here is that if you now identify that something is wrong, you need to go to that step of the intervention. And there's been a lot of recent work looking at knowledge graphs and combining knowledge graphs and explicit knowledge into large neural networks, in particular large language models. So we hope to achieve modularity, better control, querying the system, and then repeating the process. But we need to think about the stopping criteria. Right? So how many of these queries, and how many times, and what, how much probing. So this is a question mark for this line of work where we take LTN, logic tensor networks, with querying for explainability. So, as I said, this has been used to address bias and fairness, and it is a form of alignment, but it's different from reinforcement learning with human feedback. Another extension of logic tensor networks looks at the idea of this querying that I mentioned happening over time and monitoring how it's changing. So here you have in this paper this idea of continual reasoning, and you have the typical non-monotonic task of trying to learn whether penguins can fly or not. And if you break down the knowledge into stages, knowledge that goes in at this point, and then later some more, and then some more, you can monitor the querying. So here at stage 2, when the system finds out that the bird is a penguin, it will assume that it flies, but then later, when it has extra knowledge about penguins, then you can see the satisfiability level going down. So querying, modularity, and querying over time with different curriculum, right? So knowledge being provided over time instead of just once. Instead of just some knowledge becomes available, you already have some knowledge base or a knowledge graph, but you create a curriculum, you provide only parts of it, and the order in which these the curriculum, the way that this is divided will have an impact on the outcome. So that needs to be studied as well. Finally, in the context of transfer learning, I just want to say something about consistency and coherence as part of this this paper here from last year. Imagine a situation where blocks are provided as input, and all of this in the image domain. I'll say a few words about the language and text domain later. All of this in the image domain, the blocks are provided, and we can see which tower is higher. And we can train a neural network to decide, well, okay, this is doing a good job spotting that a tower of block is higher than another, or larger. And then we transition to digits. And we now want to find out if 5 is larger than 4. And this is more the way that humans will learn. So, and we don't want to start again. This idea of larger than, this concept should be applicable whether we are talking about towers or digits, even though in the case of the towers, you can measure and you have a visual cue. In the case of the digits, you don't. It's more abstract, but it's the same larger than task. And then, well, transitivity may apply, right? So if X is larger than Y and Y is larger than Z, then X is larger than Z. This could be one of the rules. So consistency across domains is precisely trying to make sense of, well, I'm going to provide all this data to this network. How can I use that, that knowledge? How can I apply knowledge that was used in one context in a different but analogous domain? And just to wrap up on the more technical stuff, recent work that I think is relevant to this community, looking at other forms of learning other than backpropagation. I think there is too much of an emphasis on backpropagation. And there are other interesting learning algorithms, such as contrastive divergence. And in this paper, we look at transfer learning in that context. Transfer, for instance, from effusion to COVID, or transferring from digits to characters, or transferring from blocks to digits, but also reasoning and using these networks, these restricted Boltzmann machines, to reason with full propositional logic. So we can talk a bit more about that in the questions and answers if there is interest. So in summary, in my view, now there are 3 ways to add knowledge into neural networks, and we touched on these. It's 1, to change the architecture. 2, to change the loss function. And 3, to tweak some of the input. And this is, maybe that's what prompt engineering is. And I don't think it's, although I can see the practical value, I don't think it's something that is very satisfying, this idea of changing and fixing some of the inputs, because we know that if I have a network with, let's say, 3 inputs, A, B, and C, and I fix A, then I'm going to get to a different place in the manifold. Now, if I have, if my inputs go to infinite, then I'm going to have many different answers for these changing initial conditions. And I think maybe that's what we are seeing when we see that a lot of prompt engineering is creating such massive variation in performance. And we know that these systems can also diverge, so maybe the hallucination stuff is a result of something like that. Small changes in the probabilities in these large networks causing big changes in the prediction of the probability of the next token. So I think what I'm trying to say here is that we should probably stick to adding knowledge by changing the architecture and changing the loss function. Now, moving on to some of the challenges, I just want to mention that the videos from the NESI workshop are available on that link there, and that there is a new journal, Neurosymbolic AI journal, if you're interested in this line of work. There have been many approaches which are now neurosymbolic recently, and that's in fact why we felt it was time to set up the journal. But there are many proposals which are more of a hybrid. So you have a neural network and you have some symbolic system, and they interact, but they are not really integrated as we would like them to be. And many approaches where reasoning, the terminology needs to be formalized properly. So I think this is all good, but it will take some time to consolidate. Interesting to see also many different benchmarks and applications in healthcare, aspects of accountability and finance. Maybe there are other interesting applications. And perhaps the killer app for the community being a chatbot where we can fact check, but not with RLHF, reinforcement learning with human feedback, because of the serious issues that have been identified to do with mental health of those involved in performing the feedback. I've decided to put a few slides here now about the risks and the challenges and the opportunities also for this community. You're probably aware of what happened to Cruise and how they had to stop their business essentially. And so this is in the context of images, right? Mostly in the context of videos, rather than multimodal. So there is certainly a need for guarantees to be provided now to these systems. But in the context of the risks, and those are mostly associated with large language models, not videos and images. And I just wanted to say a few words about what has been going on recently, to say that I don't believe that the risks are currently existential, but at the same time, and there's a link there to a talk that I gave, which was focused almost exclusively on this aspect. But they are serious. The risks are serious. They are not the risks associated with the killer robots, but they are associated mostly with disinformation at scale and risks to democracy, to this kind of stuff happening, and people being prompted by some of these systems to commit acts which are illegal. So this was an AI-generated image that created a real dip in the stock market for a few minutes, I think. So this is problematic with systems like ChatGPT deployed to 100 million users worldwide, and polluting the internet, right? With now data that is generated at scale. And so this is of course a major concern. The opportunities are immense. The the systems are very impressive, but the risks are serious and are present. They are already here. They were, in fact, already here. Decision-making by these systems is a problem without scrutiny. And so just to argue again for the idea of instilling knowledge, distilling, and repeating. So adding more control to such systems through the idea of interaction with experts using the neurosymbolic cycle. I want to give a few minutes for questions and some interaction among us. Maybe I'll leave this for the questions and answers if there are questions more focused on what's happening in terms of the disagreement among the leading AI experts and the direction that we may be taking, which is going to be bumpy in terms of regulation, and the race that is now on, taking us in a strange direction where the UK Prime Minister interviews Elon Musk, and some initiatives which are welcome, but that will need to be checked very carefully. And I would point you to this video here, TED Talk by Ian Bremmer, on some of the issues that we are seeing in front of us. So to summarize, we hope to use symbolic knowledge to control learning, adding fairness constraints and other constraints, perform even alignment. As part of this cycle, hope to derive relevant concepts and then reuse them. That has implications to continual learning and reasoning and inference in these systems. We want to have these principles of coherence, for instance, in place so that we can control also how applications change from one domain to another. And this requires a human-in-the-loop approach with tools, technological tools that allow for that interaction to be meaningful, and that's not RLHF. If we take this seriously in the next 5 years or so, the neurosymbolic approach, then that also will have to be scaled up, but hopefully with more quality than what we've seen. Huge engineering effort that needs to be praised, but also evaluated on very large or larger multitask benchmarks and environments. Right. So thank you so much. I'll stop here, and I have a couple more slides on where we are and some of the latest developments, because now, you know, the way that the field is going, we are in a situation where there is something new happening every day. But I'll share the slide. I was just saying something about the in the panel yesterday. What is nice and high multimodal. I think it's the way to go. So I was talking about images and language. The future will be multimodal, combining all of that. And there are some interesting question marks around that video as well. But anyway, I'll stop here. Thank you very much.
Let's thank our speaker. Oh, it's open to questions. Any questions? Yes.
Thank you, Arthur, for the enlightening talk. Covering technical aspects and also concluding with the risks, really interesting. And both yesterday and today, you mentioned the usage of knowledge graphs together with neural networks, and I was kind of curious about that because I'm also working with knowledge graphs to support symbolic reasoning on system engineering. And one of the issues is, of course, performance and scalability, because then you need to query these knowledge graphs, and sometimes, depending on the size and how large this knowledge graph is, may not feasible. And yeah. So when you mentioned that, I was picturing in my mind, you have the neural network, and during the algorithm execution, then you can use a knowledge graph to maybe cut some way, some processing during the algorithm. But yeah, I'd like to hear from you if you have some insights, or if you have more info on these, how these knowledge graph neural network integration, how does it happen? Okay.
Yeah, thank you. Yeah, let me answer that, and then we can go to the Gemini and Meditron and what's happening with the risks. Yeah, so the reason why I mention it is that when you see knowledge described, for instance, here in this application of LTNs, these rules that you have to query in the network, they may come from a knowledge graph. But there is a lot of other, a lot of interest from people actually converting these graphs and then creating embeddings and using graph neural networks associated with the knowledge graphs. And then there's, of course, people using the knowledge graph and what I call more of a hybrid system. You have a knowledge graph and you have a neural network. They're not necessarily doing the same thing, or one being used to create the other, but they're separate, and then you try to get an improvement by using both. And I can see that this will become, there are many practical applications of how these can be integrated, but this is the current research looking also people coming from the semantic web community into the development of these neural symbolic systems.
Arthur, I have a question, perhaps a silly one, but sorry. This question has I've been trying to even formalize my doubts, which is when we think of formal methods to guarantee reliability of systems, how trustworthy the systems are in general, we have properties like fairness, absence of deadlocks, and okay. But when we think in terms of an artificial intelligent system, shouldn't we be concerned with which kinds of properties we should seek to prove in order to say that the system is trustworthy? Of course, there are no general proofs like properties like for fairness and deadlocks for distributed systems, for instance. But at least for the kind of applications that we may have in mind, shouldn't we try to seek if that is even formalizable or provable or things like that? What do you think about it?
Yeah, thanks for that. Indeed, we may have fairness constraints, not in the sense that you mentioned, in terms of fair access, but for instance, gender balance. So then this is basically something that needs to be specified as a rule for this to work, and then checked as to whether it's being satisfied or not. So in practice, I think it becomes very much an iterative approach. So that's why I said we don't really know what the stopping criteria are. And so that in practical terms means that we need to facilitate the job of the domain expert who is in this loop, and provide such metrics like fidelity measures and so on, so that they can feel more confident validating the system. So in a way, in my mind, for instance, a medical doctor will have to learn some data science and be engaged in the development of these systems, having to have the right tools to be able to perform that interaction, because right now it's not fair, because the systems have seen more data than the doctor will ever be able to see in their lifetime. And the doctor, so placing the human in the loop should not be an excuse for saying, well, the liability lies with you. And so the interaction between human and machine needs to improve quite a bit. And I hope that we'll have to take some baby steps in that direction. But finding out what are the ingredients, what are these properties, is a very relevant research question. I don't have an answer. Coherence may be one of them. Having a more compact system, preferring a more compact system to a very large one, but I'm sure there are more.
No? Okay, Arthur, again, thank you very much indeed for your very interesting talk, and we hope to see you soon sometime. Okay, thank you. Let's thank again.
Well, I was a little bit, no, that's not true. I was completely taken by surprise when Professor Sergio Campos and Professor Lucas invited me to host the next edition of the SBMF. So if nothing changes, I hope not, the next SBMF will be in Vitória, Espírito Santo. Okay. And will be hosted by the Federal Institute of Espírito Santo, IFES. It's working? Okay. IFES is an old institution. It has 112 years of existence. Sorry. And I will not go over all the names we had in the past. It would change it a lot. But in 2008, all the technical schools were unified in a single system. They became Federal Institutes of Education, Science and Technology. And we are an institution that goes from middle education with technical emphasis to from high school to doctorate. And our institution has 36,000 students, about 36,000 students, 1,300 professors or lecturers, 22 campi. We are in roughly half of the cities in the state. We have one innovation hub, one thing called the City of Innovation in Vitória that's dedicated to foster innovation and try to stimulate the creation of startups. 36 undergraduate courses, 30 postgraduate courses, lato sensu, 11 master courses, and 1 doctoral course. Just for the matter of comparison, we are roughly the same size of the Federal University of Espírito Santo. We have more students, less professors, about the same number, not exactly the same, but close to the same number of undergraduate courses. But in the postgraduate courses, we are very behind. I myself am part of a postgraduate program that started just 4 years ago, so we are very new. My campus is in the city of Serra. It's a neighbor to Vitória, the capital. It's a beautiful camp, but it's a little far away from everything, so we are going to do the SBMF in Vitória. And, well, one reasonable question for some people is, where is Espírito Santo? Where is Vitória? We are here. Espírito Santo is here. So it's a little far away, but we have very well-known neighbors. We are neighbors from Rio de Janeiro, Minas Gerais, Bahia. Everybody knows these guys. Nobody knows us. But we hope to change that a little. Espírito Santo is divided in a few regions. Our geography is very diversified. We have dunes here, like the movie Dune. We have a region with mountains. We have a region with a little bit of other kind of mountains. We call them pontões. It's something different. We have a region of jungle, Atlantic jungle, and we have a lot of a huge littoral, a coast. So we see something like that when you arrive in Vitória. You see a big mountain, and you also see the sea and beaches and some monuments. Vitória per se is a small city. It's just this island. It has about 350,000 inhabitants, but the metropolitan region, it's about 3 million inhabitants, 3.5 million inhabitants. And this is the airport. This is where we hope to hold the symposium. So it's about 10 minutes from the airport. It's very close. And just for reference, my campus is here. It's about 20 minutes from where we will hold the symposium to my campus, if you want to go there. Manguinhos used to be a fisherman village. It's a very nice, very beautiful beach. Very good food there, a lot of restaurants. And this is where we hope to hold the Simpósio, seat of innovation. It has good installations for conference, and 180 people would be accommodated here with no problem. Space for the coffee break. We probably will not have açaí break. We are not great in açaí in Espírito Santo. I'm sorry. And so some monuments and touristic places in Espírito Santo. I will not take too long with them. Just for you guys to see that we have a good diversity of places. Oh, and we have the biggest statue of Buddha sitting outside of Asia. So who would know? And we have a lot of waterfalls. We're about 70 waterfalls in the state. There, people like to go there. Falésias, more waterfalls. And Pico da Bandeira is in the border between Minas Gerais and Espírito Santo. If you are here, you are in Espírito Santo. If you are here, you are in Minas Gerais. So it's the third tallest peak in Brazil. I believe it's the only one you can go on foot from the three highest. And